Thanks for coming to today's presentation. Today, I want to talk about computational storage. In particular, we want to discuss research questions that needs to be thoroughly reviewed for the widespread adoption of this technology in large-scale data centers. I'm Jay from Microsoft Research, and this is a joint work with Antonio from the University of Edinburgh. What is computational storage or computational storage devices? Computational storage devices are storage devices including general purpose, special purpose, or reconfigurable processing units that allow running applications inside the devices. The figure shown on the right side shows two different types of flash SSDs that we could easily see in the market. While they provide a block-oriented interface like hard disk drives, if you open up an SSD, unlike a hard disk drive, you can see that it contains embedded processor, DRAM, and flash memory. So you can think of this device as a kind of mini computer that could run any code. Computational storage architectures have numerous advantages. The primary benefit of the CS architecture is that it enables faster and more energy-efficient data processing, mainly because it could offload work usually processed by the host CPUs to storage devices. Without the CS architecture, for example, in a data analytics context, the host first needs to transfer all data from storage devices, and then it can perform its first task, like applying predicates over the data. With the CS approach, however, before moving data to the host, storage devices could take an initial step of filtering out data based on the predicates. Therefore, the amount of data to be moved and processed by the host machine could be dramatically reduced. Another benefit is that this architecture could provide more efficient and shared storage environment. With a CS architecture, we can think of a level of parallel processing that enables a microservice-like approach to running applications across all the individual devices. Such ability to process the data simultaneously could greatly reduce the time to locate and to process the desired data. Last but not least, it also helps leveraging the existing network infrastructure for much longer. Since computational capabilities enable the storage to work on a large data set by using high internal I/O bandwidth of modern SSDs, it could avoid the performance bottleneck being restricted by a network. As a result, the network interconnect would be less critical with computational storage. Actually, the idea of running applications inside storage devices is not new. For the last two decades, several projects have been conducted to explore the opportunities to run user-defined tasks on storage devices, including hard disk drives and the first generation of the SSDs. While some performance improvements or energy savings were observed, there were several challenges preventing the widespread of the idea. The biggest challenge was that the processing capabilities available inside the device were very limited by design. Low performance embedded processors, resource-constrained FPGAs, and high latency embedded DRAM. All of these require extra careful programming to run user-defined code to avoid performance limitations. Only very recently, computational storage devices, including much more powerful processing units and providing more flexible development environment, become available on the market. I'm not going to explain all the details of different CS architectures, which is discussed in the paper, but want to point out that many SSD vendors are currently manufacturing their own version of computational storage devices with multi-core general-purpose processors, FPGAs, and high-performance DRAM and flash memory. Looks great, but why still computational storage devices are not widely adopted in large-scale data centers? This is because we believe that even commercially available CSDs are still missing a wealth of functionalities that should be really carefully considered to be practically used in data centers. For example, we need to discuss more on how to handle heterogeneous resource management issues and multi-tenant environment in a secure way. And also, Still, more flexible development tools are needed for easier programming, debugging, and deploying the applications to the devices. So, the goal of this work is to discuss the most pressing open research questions that need to be answered properly to foster widespread adoption of computational storage. In this work, we try to identify such questions within the following categories, including resource management, usability, security, and data consistency. In the following slides, I will visit each category one by one. First, resource management. In a data center, we can easily imagine a server where one or more storage devices are attached. From a software point of view, this server can be viewed as a distributed system since each device has its own processing units and software stack. Therefore, it is very fundamental to provide efficient and fair usage of hardware resources, including processing units, memory, and storage. For this purpose, right resource management policies may be needed to balance the workload among computational storage devices in order to meet performance and power goals. Also, such policies are required to guarantee that no single resource is overloaded at any given time. To widen adoption, usability is certainly fundamentally important. Applications running on the device should be easy and quick to program, debug, and deploy. In particular, debugging an application that runs both on a host CPU and computational storage devices CPUs at the same time shouldn't be a nightmare. Like debugging in a distributed system, programmers might end up having multiple debuggers or log traces coming from different devices to identify problems. Another matter is whether a CSD needs to be considered as a totally independent compute node or as a storage side accelerator. In the latter case, a full-fledged workload cannot be executed on a device because the device is simply used as an accelerator, and therefore, the host CPU needs to decide which portion of the application needs to be offloaded to the device to optimize the performance. When data is read or written by the host CPU and the computational storage device's processor simultaneously, consistency problems may arise. This issue does not only apply to just data blocks. For example, when the software running on the host CPU or on computational storage device's processor creates a new file, the creation must be notified to the other CPU. Obviously, classic file systems do not address such issues, and even worse, common disk interfaces like SATA, SAS, or NVMe are not well prepared to manage such situations. In addition, a single CSD may fail during any operation, including in-surge processing. Replication, sharding, and other technologies may be used to tolerate failures other than just improving performance. Finally, security. When a single SSD stores data from different users, it is fundamental to not allow users to access each other's data. Traditionally, there are two different approaches for controlling such data access. The first is to use a file system, and the other option is to use either hardware virtualization or to use NVMe namespaces to assign different parts of the storage to different users. Like such existing protection mechanisms, computational storage needs to define secure techniques to guarantee that the code running on the device should access only what is allowed to access. In addition, the submitted code should not alter the integrity of the firmware and system software on the device. Otherwise, simply the device will malfunction. Clearly, the program models available to the programmers who want to run applications among the host and computational storage processing units largely affect the way the questions we raised in previous slides are answered. Therefore, it is very important to evaluate available computational storage program models to see how the questions will be answered when each model is used. The table shown here summarizes such evaluation. Due to the time constraint, I won't explain all the details contained in this summary, but here, The blue cell indicates the relatively being positive, and the red cell, on the other hand, represents relatively being negative. So as you can see in this table, we believe that there is no one-size-fits-all programming model that works for all kinds of applications. If you are interested in more in-depth discussions about this, please see our paper. Also, the paper includes discussions about how to deal with hardware and software interface matters. Unlike 10 years ago, currently we have several options to use high-performance computational storage devices which are available in the market. However, still they are not widely used in data centers at scale. To discuss why, we identified several open questions which needs to be answered properly. There is a standardization effort going on, but we strongly believe more research and development is needed. To foster the adoption, we also believe that we need to rethink the right program models, design extensible hardware and software interfaces, and more importantly, we need to develop open source platform with a full software package for active research and development. Thank you for listening.